And my pleasure to introduce our first speaker of the Computer Algebra and Discrete Mathematics section, Professor Vasyl Ustimenko from Royal Holloway University of London and Institute of Telecommunications and Global Information Space from Kyiv. And he will tell us about some applications of algebraic geometry to non-commutative cryptography.
Thank you, Mr. Chair. It's my pleasure to start the session on computer algebra and discrete mathematics, and I'm very grateful for giving me the opportunity to present core research of my department in Kyiv. It's written here, and we have a joint program with Royal Holloway University of London, United Kingdom. It's of course the talk will be on post-quantum cryptography. In here in Royal Holloway University of London is located the Center of Excellence for research in post-quantum cryptography. Our project is supported by British Academy, and actually I'm holding a position of research fellow and work with my department in Kyiv, actually, in fact, online. So the university is located in Windsor area. In fact, from that red building, main building of university, the connection is quite close to Windsor Palace because the University Park and Windsor Park are just joined. It's one green area, and the distance from red building to the place where King Charles is sitting is about 4 miles. So it's new, of course, research center as post-quantum cryptography is new area. The old laboratory in UK, Bletchley Hill, dealing with symmetric cryptography, and you heard about during activity on breaking Hitler Enigma. So I will start with directly from algebraic object. It's a affine Cremona group. It's defined as a homomorphism group of polynomial ring k x1, x2, xn, where k is arbitrary commutative ring with unity. So each automorphism could be given as via its values on variables. So sigma xe, so xi moving to fi x1, x2, xn, where fi is some polynomial. So we will think that this standard form for presentation of the automorphism will be kept further. And the polynomials will be given in their so-called standard form just via the list of their monomial terms ordered in lexicographical order. So we can talk about degree of polynomial fi here, and about degree of map, because it's just maximum of fi. And if we have some subgroup in this affine Cremona group, then we will talk about degree, its degree as maximal degree of its representatives. So now that's next definition. It's a bit applied nature. We assume that element sigma has a trapdoor accelerator, which is just piece of information which allow to recompute the reimage of this map for given value b in time O large from n square. So you see that if we have such sigma, it's actually acts naturally on a free module k power n. So we can talk about pre-images, and the knowledge of this secret piece of information, or maybe hidden piece of information, allow us to compute the reimage in time O from n squared. Notice that even if sigma is quadratic and given in a standard form via such list of monomials, that computation of reimage could be extremely hard problem. So it's kind of magic piece of information which will allow us to find the reimage. Of course, it's step forward to trapdoor function. So we can add that without knowledge of this T, the computation of reimage is practically impossible. For instance, NP hard problem. But for this reason, I need to use conjecture that P non-equal to NP. That main conjecture of cryptography, that class of polynomial algorithm are in fact different from a non-polynomial class of algorithm, so called class NP hard algorithm. So that the situation. So we will work today with this affine Cremona group, subgroups and sub-semigroups of this object. Actually, why Cremona group? I would like to discuss this because post-quantum cryptography is dealing with search for some reliable encryption algorithm which are resistible to adversarial attacks, which use quantum computer together with Turing machine. So why here the Cremona group is important? You know that this quantum computer, like everybody knows, heard about this machine, it can factor numbers first. And here, problem with this quantum computer that we are unable to repeat some computation twice, basically, from mathematical side of view, it's probabilistic machine. But here, when we are doing factoring problem, to check the correctness of computation, it's easily one can do it on ordinary PC because multiplication of numbers takes milliseconds. Similar problem is with discrete logarithm problem because verification of the result, it's easy. Just we need to use this equation, substitute the outcome of computation by quantum computer and check. Other classes where this powerful quantum computer has advantage in comparison with Turing machine are optimization problems where an aim function is easily computable. Neural networks or Grover-like search algorithm to look for databases to search in global information space. But the area, what is important for us of symbolic computation, looks grim for quantum computation because the verification problem is very difficult because you see such transformation xi, fi, x1, x2, xn can be given a lot of coefficients of these polynomials. And imagine that we're doing twice computation and all of those coefficients are changed. So that's why the symbolic computation nowadays are considering as appropriate tools for post-quantum cryptography. Okay, maybe I will, before some result, I will say some direction of this post-quantum cryptography. That actually this area is subdivided on several directions, so-called elliptic curve cryptosystem. Actually, we need super elliptic curves because elliptic curve crypto systems are breakable. But actually, the list of this area is coding-based cryptography, multivariate cryptography, non-commutative cryptography, hash-based cryptography, isogeny-based cryptography, where those super elliptic curves are located, and lattice-based cryptography. So this each of these directions is well justified via some NP-hard problem. So research is supposed to go on in each area. But in 2017, National Institute of Standardization Technology of USA start the standardization process for possible real-life post-quantum public keys. It's just one type of instrument because there are other asymmetric cryptographic algorithms. Actually, in July 22, 4 crypto systems are already selected for standardization, and they are all from this lattice-based cryptography. Here, the last one, lattice-based cryptography. In fact, algebraic algorithms, they are located in multivariate cryptography, non-commutative cryptography, which use groups, semi-groups, non-commutative algebras, and whatever, actually did not give fruits already. Actually, code-based cryptography is also quite algebraic because lots of codes like GOPA codes are given in terms of algebraic geometry. So these outcomes motivate algebraists to look for other ideas in this post-quantum cryptography. So during this project, the last algebraic crypto system, this is so-called unbalanced rainbow oil and vinegar digital signature scheme of multivariate nature. Actually, it was based on quadratic map. We can think that it's from Cremona group, a fine Cremona group. It was investigated and cryptanalytic instruments were found. So you can look on Eurocrypt 2021 results. So that the current situation. So algebra is supposed to start from scratch in area of public keys. Okay, so I will talk about my result in depicted in abstract. Theorem 1. For each commutative ring K of cardinality at least 3 with unity, each positive integer n bigger or equal to k equal 2 and 3, there is a non-commutative subgroup G and K of degree K, so degree is 2 or 3, in this affine Cremona group, such that each nonlinear element of G and K has a trapdoor accelerator. So we have a nice group. Especially I like case K equal 2, so we have quadratic equations. And we can compute for nonlinear representative, in fact, most of representatives are quadratic, in time O from n square. So why this statement is important and non-trivial? You see, if we have, for instance, a fine Cremona group from one variables and take transformation x going to x square and x2 going to x cube and consider their superposition, so we will get the transformation of degree 6, x goes to x power 6. So similar situation is in general affine Cremona group. If we take randomly 2 elements of this group, then with big probability close to 1, of course, the composition of them has degree which one can compute as product of first transformation and second transformation. So here we have a group, a family of groups, such that roughly representatives of this group are quadratic, and superposition of these elements is quadratic again. So it gives opportunity to compute products, for instance, of n different representatives of this group in polynomial time. So it gives us the possibility. No, in fact, these families of subgroups are large in some sense. For instance, inductive limit of GNK n equal to 3 and etc. is well defined, and going to infinite object, even ring K is finite, because for cryptography, the case when K is finite field, of course, the most important one. Okay, so how we can use this group? Because this group were constructed explicitly. So this maybe first I will skip introduction and maybe some definition. So trapdoor accelerator is also already given. Okay, we can take sigma from this GNK, transform it to L1 sigma L2, where Li are elements of a fine general linear group L and K. So this is standard trick of cryptography, and use it as encryption tool. So we have free module Kn and can treat its elements as messages written in the alphabet K, and using this polynomial f for encryption, and assume that two correspondents, Alice and Bob, usually in cryptography, they share this f and share that trapdoor accelerator T. Then they can work with plain text X from Kn, use Fx as a ciphertext image under F, and encryption and decryption will cost, in fact, O(n) square. O(n) cube we will get if trapdoor accelerator T is not known for encryption. But it's important that we can, Alice and Bob can decrypt in time O(n) square. Okay, but what can do adversaries to break this system? Okay, so we think that Alice and Bob, they are keeping their linear maps Li and that trapdoor in secret way. So adversary has to use espionage for getting many pairs of kind plain text and corresponding ciphertext, and start the approximation of the inverse map f-1. No, in here in this case we have fixed degree 2 and 3. In case k equals 3, such approximation can be done in time O(n) to 10th power. But to start this problem, the adversary has intercept something like cubical number C, the constant times n cube, pairs, plain text, ciphertext, if in case n is 1001 kilobyte information, it's quite a huge number of interception. So it's a kind of good algorithm, but here we can see the option for the improvement. It's nice to have situation when element sigma from affine Cremona group has bounded degree, but the inverse is not of the same degree, and its degree is huge. That actually looks attractive, this situation. So how to use this symmetric algorithm in practice? We need to support it with the protocol, and I will present here twisted Diffie-Hellman protocol. Actually, it will be formulated for abstract semigroup, yes, but we will use this group G and K of quadratic transformation. So Alice and Bob share element G from this group and invertible element H. In our case of group, both of them, of course, invertible. So this agreement about G and H going via open channel. Alice takes positive integers K, R, A, and R, A. She raised G to power Ka and conjugate with H power minus Ra, Ra. So she getting Ga, this transformation, and she sends this transformation to partner. Bob doing similar job. He is taking Kb, Rb, own private numbers, form Gs, rising G to S power, conjugation with element H power P, and getting Gb. And he sends it to Alice. On final stage, what Alice and Bob are doing, Alice obtained Gb. She has these powers Ka and Ra, so called T and D. She compute this element X as H minus D, GBT, GD. And Bob got from Alice Ga. She raised Ga to S power. S is his private number, and conjugate with HP. And it's easy to see that it's the same element. So they share the huge element, for instance, from this group G and K. So the security of this generalization of no Diffie-Hellman protocol keeps on the conjugation power problem, because they're sending Ga and Gb via open channel. So what adversary can do? She can take Gb or Ga as B and consider equation with two variable x and y, h minus x, gy, hx, because G and H are known for him or her, and trying to get this number after, of course, system is broken. So, but in situation when we have symbolic computation, that conjugation power problem is NP hard. Nowadays, nobody knows how to solve this problem when G and H are elements from Cremona group given in the standard form. So quantum computer, Turing machine, they both could not do the corresponding job. So why this X is important? Actually, it could be used for transportation of the encryption rule. After the conducting of this protocol, Alice can create sigma from G and K with trapdoor accelerator, T known for her. can deformate it via L1 and L2 from AGL and create the polynomial transformation F and send F plus X to Bob. It's like one-time pad, absolutely secure trick. Bob knows X because they elaborate this X via the protocol, and they can use this F for encryption. The difference of this scheme is that trapdoor accelerator is known to Alice, but not to Bob. So Bob encrypts in time O n cube, but Alice decrypts in time O n square because of her knowledge about the trapdoor accelerator. Okay, so that one of the possible applications, like symbiotic combination of the protocol and encryption algorithm. We can make it a bit harder because this group platform, so-called GNK, can be expanded to some semi-group of quadratic transformation, such that in important case of finite phi, that subsemi group contains element of exponential period bigger or equal qn minus 1, n is size of the space. Why is this important? Because here we can raise g in huge powers. So this protocol looks very strong. Of course, it's a bit add some complexity, but it's very useful to have such situation. And other remark that semi-group, in fact, preferable than group in this algorithm, because for groups, ordinary Diffie-Hellman is broken in case of cyclic groups ZP star, but for semi-groups, you see we here did not use inverse of this G. It's still kind of wait for appropriate cryptanalysis. So it makes this theorem 2 makes the algorithm is much stronger. Now, actually, what we can do next theorem that we can take Cremona group over finite field FQ that works in characteristic to S, and we can create the automorphism sigma of exponential order Qn minus 3 bigger or equal than Qn minus 3 with a fine trapdoor accelerator. So it's much better that we have, say, quadratic transformation, and the inverse is huge. For instance, if we have q2 power 62, the degree, polynomial degree of inverse is 2 power 63 at least. So it's good candidate for the public key. So correspondents can use Li from a general affine group, and for public key, just Alice computing the standard form and nothing in publicly, not sending. Each public user can use this scheme. So this way we have the candidate to new multivariate crypto system. So it's good assignment for cryptanalysts because it can works. It looks solid. There are some heuristic arguments on the capability of this system, but we have a word now. We need to look at practical solution. So it's easier to make this F and execute this protocol, twisted Diffie-Hellman, and X plus F will be sent from Alice to B. Not make it public, so to make this public key in a shadow. That is a solution, which is actually several specialists like this trick. And maybe last, I have just some moments for the idea of constructions of these groups and how algebraic geometry is used. The following scheme is used. We are taking projective geometry over finite field. So it's union of Grassmannian with incidence relation I. After we are taking unitriangular matrices group, and we have binomial coefficients and m orbits on this set, so-called Schubert cells. Each Schubert cells is a vector space. We are considering the Schubert geometry disjoint union of largest Schubert cell. For each Grassmannian, there is a unique large Schubert cell. And in this geometry, doing some following trick. Actually, projective geometry can be defined over a ring. So we can change finite field for commutative ring FQX1, X2, Xn. And use general element from largest Schubert cell X1, X2, Xm. Consider this Schubert geometry as Kx1, Xn. And after consider a round walk starting from X1, X2, Xn, we are going to via some round walk. So we need to return to this Schubert cell Si. And destination point will be some polynomials f1, f2, fm. And what we are doing, we maybe g1, g2, gm, and we are taking endomorphism xi, gi, x1, x2, xm of a fine Cremona semigroup. Of course, we need to work to find the condition when it will be automorphism and condition when we have quadratic automorphism, that this is a general idea. And some final remark about Schubert, which was not a composer, because you know the well-known Berlioz, who was not a composer in Master and Margarita, was actually beheaded in Moscow. But Hermann Cäsar Hannibal Schubert is real person, a great mathematician, a father of computational algebraic geometry. So it's not a fiction story. So thank you for your attention. That's all. Maybe there is some small time for questions.